Hello everyone, I welcome you all to my YouTube channel. So today we are going to start the pi sigma positive charge delocalization, and I have taken these questions to teach you this concept. Okay, so let us not waste much time and move to the first question that we have in hand. Alright, so the first one is this: a benzene ring with CH2 and positive charge. So there is a special name of this carbocation. This is a carbocation because a positive charge resides on a carbon atom, and the carbon here has a does not have a tetravalency. It has the covalency of 3, so it has a true positive charge. So this is a carbocation, and we have this special name of this carbocation. This is a benzyl carbocation. Alright, this is a benzyl carbocation. Now the first question is, this carbon has a positive charge, and you know that alkyl substituents are electron donating in where? These are electron donating in inductive effect when we talk about. Now this carbon has a positive charge, so this is sp2 hybridized, and all these carbon atoms are also sp2 hybridized. So the first question is whether the CH2 positive group will act as an electron donating group here, or whether it will act as an electron withdrawing group with respect to mesomeric effect or resonance. The question is whether the CH2 positive shows a minus M effect or a plus M effect. When a group shows a minus M effect, it pulls away the electron density towards itself, right? मतलब benzene ring से CH2 की तरफ जाएगी electron density if it shows a minus M effect. If it shows plus M effect, तो कार्बन की जो electron density है वो रिंग की तरफ आएगी. Now you think about it yourself. कार्बन के पास तो ऑलरेडी इलेक्ट्रॉन डिफिशियंसी है, इट हैज अ पॉजिटिव चार्ज, तो अगर जितनी भी इलेक्ट्रॉन डेंसिटी बची है वो रिंग की तरफ दे देगा तो उसकी इलेक्ट्रॉन डेंसिटी तो और ज्यादा इंक्रीज हो जाएगी. इट विल बिकम अनस्टेबल, हाईली अनस्टेबल, सो इट वोंट शो अ प्लस एम इफेक्ट. प्लस एम का स्कोप खत्म. बट माइनस एम इफेक्ट, अगर वो रिंग की इलेक्ट्रॉन डेंसिटी अपनी तरफ ले ले तो ये पॉजिटिव चार्ज कार्बन के ऊपर से खत्म हो जाएगा. इट विल डीलोकलाइज ओवर दिस बेंजीन रिंग. This is the concept of delocalization, right? So this carbon with a positive charge will show a minus M effect and takes away the electron density of this phenyl ring towards itself. So this is a benzyl carbocation. A benzene ring with a CH2 moiety is known as the benzyl group. Okay, so let us see how we can draw the resonance contributor of this. I know you have some idea how we are going to draw the contributors. We draw the arrows from electron rich to electron deficient centers. So this is a pi bond, this is a sigma bond, this is a positive charge, right? So we will move the pi electrons towards this positive charge, and we will not move positive charge to this. This is wrong, but this is right. Okay, remember this. Now the first contributor will be here. This pi bond shifts here, okay, and we'll have the first contributor, CH2. The positive charge of this carbon has got neutralized because here carbon had a valency of 3, a covalency of 3. It was trivalent here, but now carbon has gained its tetravalency back. So carbon does not have any charge here. It is an uncharged moiety, uncharged species. So a pi bond here, a pi bond here, and a positive charge has come here because the pi electrons have shifted from this bond to this bond. Now to stabilize this positive charge, this pi bond shifts here. Double bond CH2, double bond, and a positive charge over this carbon. Now to stabilize this positive charge, this pi bond shifts here. As you can see, this is an example of linear conjugation, right? Positive, one contributor. Since one contributor is involving the other electron rich species in resonance, so we call this as the linear conjugation. All groups are in resonance with each other. This to stabilize this positive charge. Now this bond comes back in the benzene ring, and we have CH2 group back with a positive charge. Okay, so this benzyl cation we have got back. Let us draw the hybrid. I know you have learned how to draw the hybrid. I'm just drawing for my practice. Here we have a double bond character development, CH2, and now this bond will have this ring will have partial positive character development, where at ortho and para positions, partial positive here and partial positive on this carbon also, because in the initial structure we had a positive charge here. This is the hybrid of benzyl carbocation. A benzyl carbocation is very stable because it is stabilized by resonance. Okay, so this is a special type of carbocation which is very stable carbocation because it is stabilized by resonance. Stabilized by resonance. Now let me just recall that if I add a nucleophile, where will it attack? On this carbocation. If I am just considering this phenyl ring, and let us forget about this CH2 with a positive group, where will this nucleophile attack? This nucleophile will attack at ortho and para position if it is allowed to attack only on the ring. Okay. Now let us see this system. This system is, you already know what type of system is it. This is an allyl carbocation. Allyl carbocation. Allyl carbocations are also very stable. Okay. Allyl carbocations are also very stable. They are stabilized by resonance because there is a pi sigma resonance. There is a pi sigma positive type delocalization possible here. So allyl carbocations are also highly stable carbocations. There is a pi bond, sigma bond and a positive charge. All three being sp2 hybridized, their p orbitals are aligned parallel to each other and delocalization is possible. You can draw the resonance contributors easily. Just shift this pi bond here, the positive charge will come here. So the positive charge is equally spread on this carbon and on this carbon. Okay, this carbon is relatively electron rich, so the hybrid will be pi character here, partial positive here and partial positive here. This will be the hybrid of this allyl carbocation. Just see, this carbocation is, if you see here, this is what type of carbocation, primary, secondary or tertiary? This is a secondary carbocation. Okay, and here we have this carbocation is primary. Which one is more stable, secondary or primary? Secondary is more stable. अगर आप inductively देखो तो the order is secondary, tertiary carbocation is most stable, then secondary, then primary. Okay, these are secondary. This is secondary carbocation, this is primary. Both of these carbocations are not much very stable if you see only the saturated systems, but here we have an unsaturated group in resonance with this positive charge, which makes this special secondary type of carbocation and this special primary type of carbocation much more stable, and that's why we have taken the example of benzyl carbocation and allyl carbocation here in resonance. Okay, now let us talk about this structure. This is very important. What is the name of this cation? This is made from, this is made when aniline gets protonated. This is aniline na? This nitrogen atom, this aniline is basic. When we subject aniline to an acid, we get this. If I subject aniline to an acid, I get this. If aniline is the base, this is the acid, this proton comes from acid, what will be this? This is the conjugate acid of aniline, right? This is the conjugate acid of aniline and its name is anilinium ion. Anilinium ion, anilinium ion. All right. So just tell me, is there resonance possible between phenyl ring and NH3 positive group? क्या ये पाई इलेक्ट्रॉन्स उधर शिफ्ट होंगे नाइट्रोजन के पॉजिटिव चार्ज को स्टेबलाइज करने के लिए? क्योंकि अगर ये पाई इलेक्ट्रॉन सपोज इधर शिफ्ट हुए तो फर्स्ट कंट्रीब्यूटर आपको क्या मिलेगा? फर्स्ट कंट्रीब्यूटर यू विल गेट एज दिस NH3, और ये पॉजिटिव चार्ज आपको लग रहा है खत्म हो गया, ठीक है। बट क्या ये स्ट्रक्चर वैलिड लुईस स्ट्रक्चर है? क्या ये एक रेजोनेंस कंट्रीब्यूटर होगा? इफ यू सी हियर, नाइट्रोजन हैज एक्सीडेड इट्स covalency beyond 4 and nitrogen can never do this because it does not have extra d orbitals to accommodate the extra charge. उसके पास नाइट्रोजन के पास तो सिर्फ 2p ऑर्बिटल्स तक ही होते हैं, उसके पास एक्स्ट्रा ऑर्बिटल्स ही नहीं है एक्स्ट्रा चार्ज अकोमोडेट करने के लिए, तभी नाइट्रोजन डज नॉट हैव अ कोवेलेंसी बियॉन्ड 4, बट इधर एक्सीड हो रही है, कोवेलेंसी इज 1 2 3 4 5, इधर कोवेलेंसी 5 हो गई नाइट्रोजन की। इट इज एन इनवैलिड लुईस स्ट्रक्चर, इनवैलिड लुईस स्ट्रक्चर। तो अगर आप बोल रहे हो कि NH3 पॉजिटिव ग्रुप -m इफेक्ट दिखाएगा क्योंकि पॉजिटिव चार्ज अगर आउटसाइड द रिंग है तो वो -m इफेक्ट दिखाता है, सो यू आर रॉन्ग। इधर मीजोमेरिक इफेक्ट नेगेटिव नहीं होगा और ना ही पॉजिटिव होगा, पॉजिटिव का तो सवाल ही नहीं क्योंकि नाइट्रोजन के पास लोन पेयर नहीं है, ठीक है। बट इधर ओनली इंडक्टिव विड्रॉल ऑफ इलेक्ट्रॉन्स होगा, ओनली -i इफेक्ट विल बी देयर। NH3 positive is a strong electron withdrawing group ना, there is a YouTube short uploaded on my YouTube channel, you can refer to that. Only -i effect will be possible here and no -m effect will be there. Okay, so don't write कि इधर रेजोनेंस की वजह से एनिलीनियम आयन इज ऑल्सो स्टेबल, ठीक है, ये स्टेबल एनिलीनियम आयन रेजोनेंस की वजह से नहीं हो रहा। दिस इज अ वेरी वेरी स्पेशल टाइप ऑफ कार्बोकेटायन, वेरी स्पेशल टाइप एंड अ हाईली स्टेबल वन ऑल्सो, ठीक है। अगर इस तरीके का स्ट्रक्चर होता है ना हमारे पास, this 7-member drink is actually a little difficult to make. So if we have this structure, its name is tropyllium bromide, tropyllium bromide. This is what? This is an alkyl halide na? So this is a tropyllium bromide and you should know that this is a solid at room temperature, this is a solid. अब अगर solid होता है तो इसका क्या मतलब होता है कि उसकी पैकिंग, इट हैज एन आयनिक पैकिंग, ठीक है, आयनिक पैकिंग है, उसमें केटायन और एनायन अलग अलग एग्जिस्ट करते हैं, केटायन एंड एनायन अलग अलग एग्जिस्ट करते हैं डिफरेंट लैटिस पॉइंट्स पर, ठीक है, तभी तो सॉलिड होता है, आयनिक पैकिंग हो पाती है, CCP HCP यू स्टडी इन सॉलिड स्टेट ना। तो अगर ये कोवेलेंट कंपाउंड पॉजिटिव और नेगेटिव अलग अलग आयंस के तौर पर एग्जिस्ट कर रहा है, सो इट मीन्स कि उसका पॉजिटिव चार्ज स्टेबल होगा, और यही आयन है जो पॉजिटिव की फॉर्म पर इंडिविजुअली स्टेबल रहता है और ब्रोमाइड नेगेटिव की फॉर्म पर अपने लैटिस पॉइंट्स पर प्रेजेंट रहता है। ओके, सो ट्रोपाइलियम ब्रोमाइड इज अ सॉलिड, और वो सॉलिड होता है इसलिए क्योंकि उसका केटायन, एनायन तो स्टेबल है ही क्योंकि हेलाइड्स जो हैं दे आर एक्सीलेंट लीविंग ग्रुप्स, राइट, दे आर इलेक्ट्रोनेगेटिव एंड सो दे कैन अकोमोडेट द नेगेटिव चार्ज वेरी इजीली, तो वो तो स्टेबल है ही हेलाइड्स नेगेटिव चार्ज के साथ। बट ये केटायन, ये कार्बोकेटायन है और ये भी एक्सेप्शनली स्टेबल रहता है, एक्सेप्शनली स्टेबल। इसकी स्टेबिलिटी के बारे में वी विल स्टडी व्हेन वी विल डील विद एरोमेटिक्स। ओके, जस्ट रिमेंबर इट्स नेम इज द ट्रोपाइलियम cation. It has pi sigma positive charge delocalization happening. Okay, this positive charge, okay, let us draw the contributors. To stabilize this positive charge, this pi bond comes here. Okay, positive charge here, here and here. These are two bonds. When this bond comes here, positive charge comes here, double bond here, double bond here. Okay, to stabilize this positive, this comes here. Positive here. Now to stabilize this positive charge, 1, 2, 3, 4, 5, 6, 7, 7 positive. Sorry. Okay. So these are the different resonance contributors. The positive charge is spread over this ring. So this is the hybrid. 1, 2, 3, 4, 5, 6, 7. And you can draw positive charge over this circle, between this circle, if the positive charge comes, if there is partial positive on all carbons. ठीक है, तो ऐसे भी आप हाइब्रिड बना सकते हो, और अगर आप partial positive हर कार्बन पर लिखो that is also okay, या फिर positive इधर नीचे बना दो बीच में, तो that is also okay. Different ways of representing the hybrids. Now this is cyclopropynyl cation. This is again exceptionally stable carbocation. There are different reasons why this carbocation and this carbocation are exceptionally stable. We will deal with such systems and more when we'll move to aromatics. Okay, so this is stable because all these carbons are sp2 hybridized and there is resonance taking place. When this pi bond shifts here, the positive charge comes here. To stabilize this positive charge, the pi bond comes here. Positive charge here. Okay, and to stabilize this positive charge, the pi bond comes here. So there is complete delocalization of positive charge, and we are again drawing the hybrid as this. और partial positive आप अगर तीनों vertex पे बनाओ तब भी it is absolutely okay. There is no harm in it. Okay, so here we have completed the pi sigma positive charge delocalization. All the questions have been completed. Okay, there is one important case left. Here we have a positive charge here, but इधर अगर आप देखो तो ये इतना ज़्यादा stable नहीं रहता. इधर delocalization तो है, but it is not much stable. Okay, about this also, this is also a special type of compound, special type of molecule, and we will study about this concept later. Okay, इधर delocalization है, but इसकी instability का reason भी इसकी delocalization ही है. Okay, तो इसके बारे में हम पढ़ेंगे आगे, but it is really interesting. Okay, just remember it. Now pi sigma negative charge. So the first is O negative. This is the very famous phenoxide ion. This is the conjugate base of phenol. Conjugate base कैसे बनाते हैं? अगर you take phenol because it is acidic, and when you subject it to a base, the base abstracts the proton here because this is acidic, this is the active proton, and here we'll get this is acid, this is base, so this is the conjugate base, this is phenoxide, and the stability of conjugate base decides the strength of the acid. So this phenoxide ion is stable because of resonance, and hence phenol is acidic in nature. Okay, let us see the contributors. This negative charge, now there is negative sigma positive. When this negative comes here, a pi bond shifts to the other carbon and we get this negative charge, double bond, double bond. Okay, Now move this negative charge forward. Negative charge here, double bond O here. Okay, now this negative moves here, this pi bond comes back, comes to this carbon, and we get this contributor, double bond O. Now when this negative comes here between these carbon atoms, oxygen pulls back its electron density in the form of negative charge, and we get the phenoxide anion back in picture. Okay, so this is the phenoxide. These are the contributors of the phenoxide ion. Okay, the hybrid being partial negative here on oxygen, partial negative here, partial negative here, partial negative here. Okay, so just remember, आपने देखा था कि यहाँ पर जिन सब्स्टिट्यूएंट्स के पास पॉजिटिव चार्ज था, फॉर एग्जांपल CH2 पॉजिटिव, वो एक -m इफेक्ट दिखा रहे थे हमेशा, बट इधर जब भी हमारे पास सब्स्टिट्यूएंट्स के पास नेगेटिव चार्ज आ जाता है जो डायरेक्टली लिंक्ड हो बेंजीन रिंग से या फिर किसी भी पाई सिस्टम से, दे विल शो अ +m इफेक्ट. दे विल मेक द benzene ring or the pi system more electron rich by sending away the pi electron, sending away the extra charge away from them. ठीक है, अगर पाई सिस्टम से जो डायरेक्टली एटम अटैच्ड है उसके पास नेगेटिव चार्ज आ जाए तो वो पॉजिटिव +m इफेक्ट दिखाता है, एंड इट मेक्स द पाई सिस्टम इलेक्ट्रॉन रिच. नाउ दिस इज द cyclopentadienyl system, cyclopentadienyl anion, cyclopentadienyl anion. It is also highly stable type of carbon ion. Okay, there are different resonance contributor of it. If you compare this and this, this is cyclopentadienyl anion, this is cyclopentadienyl cation जो हमने पहले देखा था इधर, cyclopentadienyl cation. ठीक है, cyclopentadienyl cation में पाई सिग्मा पॉजिटिव चार्ज डीलोकलाइजेशन हो रही है, cyclopentadienyl anion में पाई सिग्मा नेगेटिव चार्ज डीलोकलाइजेशन हो रही है. दिस इज हाईली स्टेबल, बट दिस इज नॉट स्टेबल. ये स्टेबल नहीं है, जबकि इधर भी डीलोकलाइजेशन है, इधर भी डीलोकलाइजेशन है. इनके रीजंस वी विल नो इन द लेटर वीडियोस, अपकमिंग वीडियोस. बट इधर आप रेजोनेंस कॉन्ट्रीब्यूटर्स इसके बना सकते हो बहुत इजीली, जैसे आपने पहले बनाए. नेगेटिव चार्ज को यू जस्ट मूव फॉरवर्ड, जब ये इधर आएगा तो ये इधर जाएगा, फिर नेगेटिव चार्ज इधर आएगा तो ये इधर जाएगा, और फिर हाइब्रिड आप आराम से बना सकते हैं. और कॉन्ट्रीब्यूटर्स भी, दिस इज अ होमवर्क क्वेश्चन. partial negative here and negative charge spread over all carbons, and so the hybrid is drawn like this. And similarly you can draw partial negative इधर, अगर आपको रिंग के बीच में नहीं बनाना तो that is also okay. इधर नेगेटिव चार्ज हम रिंग के बीच में सर्कुलर डीलोकलाइजेशन के बीच में कोई चार्ज तभी लगाते हैं जब हर कार्बन के ऊपर सेम चार्ज आ रहा हो. अगर इस तरीके का है, पॉजिटिव इधर आ रहा है, पॉजिटिव इधर, पॉजिटिव इधर, तो आप सर्कुलेशन में पॉजिटिव चार्ज तब नहीं लिख सकते, तब आपको पार्शियल पॉजिटिव ही यूज करना पड़ेगा. ठीक है, यहाँ तो हर कार्बन के ऊपर अगर आप इसके कॉन्ट्रीब्यूटर्स बनाओगे तो सबके ऊपर नेगेटिव चार्ज आएगा, तभी आपने सर्कुलर रिंग के बीच में, सर्कुलर डीलोकलाइजेशन के बीच में नेगेटिव कंप्लीट चार्ज लगा दिया. ठीक है, नाउ दिस इज एन एग्जांपल ऑफ क्रॉस कॉन्जुगेशन. अगेन ये इधर भी डीलोकलाइज हो सकता है, इधर भी. Again, this is a homework question. You try it because we have already taken up so many questions of delocalization. You can really well do this. I know. This is another anion. This is also an example of cross conjugation. Now let us see the contributors of it. When this negative charge comes here, this pi bond will shift here. Negative here, double bond CH2 here, and this pi bond remains here as it is. Okay, now if this is pi sigma negative charge here, pi sigma, pi is also possible. When this comes here, this will move here. Okay, so there is another contributor of it, negative here, and CH2 negative here, and a positive here. Okay, so when this pi bond comes here, इधर पॉजिटिव चार्ज आया, और ये जब पाई बॉन्ड इधर शिफ्ट हुई तो यहाँ नेगेटिव आया, और ये तो इधर लोकलाइज्ड ही रहा. ठीक है. अब स्टेबिलिटी ऑफ रेजोनेंस कॉन्ट्रीब्यूटर इज ऑल्सो अ थिंग. स्टेबिलिटी ऑफ डिफरेंट रेजोनेंस कॉन्ट्रीब्यूटर्स. Stability of resonance contributors. This we will see in the next video. Okay. When we'll deal with pi sigma free radical. This is the last case of delocalization. We will study about in the next video. We will see pi sigma free radical type delocalization, and we will also study about stability of different resonance contributor, and then we'll move on to different more important concepts. All right. So thank you so much for watching. That's about it for today's video. Let us meet in the next video with a new topic.